Okay, so associated with every square matrix is a determinant. It's just a square matrix has a, do y'all remember hearing that last year, determinant? Okay. And a 2x2 determinant, of course, is easier than a 3x3, and 3x3 is easier than a 4x4. Let's say you've got matrix A, and we're going to look at a 2x2 first. Matrix A has elements 1, -2, 3, -5. The notation for determinant, you're going to see DET A, or you may just see vertical bars. So if you see vertical bars around elements and not brackets, this indicates that you were to find the determinant. All right, does anybody remember how you do that for a 2x2? All right, what you're going to do is multiply from the top left to the bottom right first. So I get -2. There's a minus sign. Well, you're going to subtract whatever you get when you multiply this way. So then multiply from the bottom left to the top right, you get -15. And then this will give you 13 for your determinant of A. So 2x2, multiply this way, subtract product you get when you multiply that way. Okay, for a 3x3, there's two ways that we're going to look at. The first way is the multiplying diagonally, both directions, just like we just did with a 2x2. So let's say you've got matrix B. All right, what you do in this case, you have to rewrite your first two columns out to the right. So that's your first step, rewrite. And this is just, this method, we'll call it multiplying diagonally. So rewrite first two column of numbers. All right, from this point, you are going to start in the top left, just like we did in a 2x2. We always start at the top left number, and I'm going to multiply diagonally all the way through till I get to that bottom right number. Just like here, we started top left, ended at the bottom right. Hey, Evan, how about like your laptop, something like that? Like I know you're probably finishing all your work like this week, but just have it out at least. Okay, when the products that you get, like I'm going to get positive 10 here, 18 times 2, 36. I'm going to get 0. I add all of those products together, and that's going to give me 46. All right, then you're going to start at the bottom left, just like we did in this matrix. I'm going to start with the bottom left, go that way, and you keep going till you get to the top right number. Somebody asked me the other day, like, what about the 0 and the 5? But notice the 0 gets multiplied here when you rewrote that column. 5 gets taken into account here. So write your products. This is going to give you positive 20. You get positive 24, 0, and add all of those together, and you get 44. Similar manner to a 2 by 2. The product you got when you multiplied this way from top left, bottom right, which in our case would be 46. You put that number first and subtract the sum of the other products last. So the determinant of B is 2. All right, the other method that we're going to talk about for a 3 by 3 is called expansion by minors. Okay, the minor of an element, minor of any element in a matrix, is the determinant left when you delete the row and column it's in. Okay, so for example, if I had this determinant, notice the vertical bars tell me it's a determinant. I mean, it's also a matrix. Let's say that I've got this first row. If I'm looking at 1, I'll have 1 here. The determinant left over after I delete this row, delete this column that it's in, is 5, -6, 7, and 8. And then you, of course, so you would calculate that. What you have to be mindful of that's very confusing, still kind of throws me off too to this day. Whenever you're figuring out the minor of any element, so, and you use rows, we're going to use rows. You can work in the first row, second row, or third row, does not matter. 1, the sign in front of 1 is going to be positive. You put a positive or plus sign in front of minor whose sum of its row and column is even. So I'll put a positive or plus sign when the sum of the row and column is even. So for example, 1 was in column, it was in row 1, column 1, so that's even. So I put a plus sign. Expansion by minors is definitely not my favorite thing, but we show you expansion by minors because that's the only way you can calculate a, well, it's not the only way you can do a 4x4. You do have to use minors, so anyway, but you'll see expansion by minors in higher level math too, like calculus and some other courses in college. All right, so you put a negative sign or minus sign, negative minus, in front of your minor if the sum of row and column is odd. Negative or minus sign if the sum of the row and column is odd. Okay, so let's look at one that is a 3x3, and we're going to expand it by minors. All right, so your steps. The first thing is you pick any column you want to. Pick a column. So we're either going to pick the numbers in column 1, 2, or 3 to be our minors. Pick a column to work with. I usually always pick the first column, but you can pick the second or the third. It does not matter. So let's choose column 1. All right, so what you do now, let's look at the numbers in this are 6, -3, and 1. Then you go through, we have to figure out, does 6 stay positive? Do I put a plus sign here? Or is this going to be a minus and make it negative? Same thing with -3. I have to figure out, is this plus -3 or minus? And the same thing on the end. And the way you determine that, look at what column and row 6 is in. 6 is in column and row 1. Row 1, column 1. So that is even when you add that together. So it stays positive. So that's +6 or +6. -3 is in what? Row 1, column 2. And so row 1, column 2, that's odd. So this gets a minus sign. And then 1 is in row 3. That was in column That was row, I got that backwards. Row 2, column 1, sorry. Row 3, column 1, that's even. 3 plus 1, 4, even. So this is plus. So that's what I always do. I pick a column, and before I do any deleting rows, deleting columns, I determine what sign those numbers get. Then what you're going to do from this point is you say positive 6 times the determinant that is left. Like when I delete this row and this column, I'm going to delete that row and that column that contains 6. And I'm left with -5, 3, 2, and 0. All right, now for -3, you're going to do the same thing. Delete the row and column that contains -3. So delete that column. I'm going to delete this row. So the determinant that's left is 4, 0, 2, 0. All right, what determinant will +1 have? If I delete that row, that column that contains 1, we're left with 4, 0, -5, 3. All right. Then your second step is simply to go through and we're going to calculate each second order determinant. So this is going to give me 0 minus 6, which is -6. This gives me 0 minus 0. And this gives me 12 minus 0, just 12. Last thing, then you're going to multiply the +6 times that, and then you're going to say minus -3 times that plus 1 times that. That's what you have left. So this will be -36. This is 0. And this is 12. So -24 is your determinant. We'll say C. Did y'all expand by minors last year? Okay. I don't know, Emily, if I showed y'all by minors or not. I know I showed you the multiplication way. Yeah. Okay. Okay, so knowing about determinants leads us into inverses. of matrices. I know last year you found the inverse of a 2 by 2, and what's new in pre-cal is we found the inverse of a 3 by 3. And you're absolutely going to love doing that because it's very long. Okay, so let's look at a 2 by 2 first. All right, let's say you got matrix A with some elements A, B, C, D. Your formula for finding the inverse of a 2 by 2, or well, this is what you, okay. In order for an inverse to exist in a 2 by 2, you have to check the determinant first. So you'd have to multiply this way, subtract product that you get from that way. So determinant, make sure the determinant is not equal to 0, because if it is equal to 0, then you have no inverse. If your determinant value is 0, you have no inverse. If your determinant value is not equal to 0, then you do have an inverse. So since you're using determinant to check, well, that's also part of your formula. So it kind of works out for you because A inverse is 1 over your determinant value. So you have to make a fraction after you find determinant is not 0, make a fraction out of that, and you're going to multiply that to your new elements you get. You're going to swap places with A and D. These switch. Then you're going to change the sign of B and C. So change the sign of these elements. Once you multiply those new elements by this fraction, you will have your 2 by 2 inverse. All right, let's go ahead and practice with a 2 by 2. Given matrix D, find D inverse. So the first thing you have to check is your determinant. So find the determinant of D and make sure it's not equal to 0. So multiply this way, and that's going to give you positive 15. Multiply this way, that's going to give you negative 7. Determinant is 22. So we're good to go. It does have an inverse. All right, step 2, you're going to say 1 over that determinant, so 1 over 22, times your new matrix that you get when you, which elements are going to swap places? Good, so these elements here are going to swap places, and what happens to -1 and 7? Good. Those change signs. So you're gonna have +1, -7. And then all you have to do from here to get the inverse is just distribute the 1 over 22. So in a lot of inverse matrices, you're gonna have nasty fractions left. So when I distribute, I'm left with -5 over 22, 1 over 22, -7 over 22, -3. Okay, one reason we're looking at inverses is because we're going to use them, like all this is building on top of one another. We're going to use them to solve some matrix equations that are not just adding and subtracting like you guys did in 8.3. All right, do y'all have any questions so far? Don't know. Just wait till we get to the 3x3 inverse. You might not like me too well after that. All right, I'll tell you what, really quick before we get to a 3x3, I need to talk to you about multiplicative inverses. If they ask you if two matrices are multiplicative inverses of one another, then you're going to multiply your matrices together. If your answer is what we call the identity matrix, do you guys remember when we did that Gauss-Jordan method by hand? And like for a 2x2, we had ones along the diagonal, zeros everywhere else. For a 3x3, you had ones along its diagonal. And of course, 4x4, and it gets so on. So if you multiply any two matrices together, and this is the result you get, ones along the diagonal, zeros everywhere else, then you would say, yes, they are multiplicative inverses. If that's not what you get, then you would say no. What? Yeah. Yeah. And I'm gonna go back over it like next week too, so because I know it's a lot, especially this next part. You've never done an inverse of a 3x3. The last couple things we're doing is not fun. Welcome to pre-cal. Okay, so for a 3x3 inverse, If you, who'd you have, Miss Rogers? Miss Shields? Okay. Okay, so this goes back to, this is kind of goes back to the Gaussian elimination that I showed you guys in 8.1. You're going to have a 3x3 matrix, and we're going to perform row operations just like we did in 8.1 when you multiply a row by something, add it to another row, you switch rows, add, subtract rows from one another, whatever. You're going to keep doing that until you want your result. So this is your starting point here. That's what we're going to start, and we want our result to look like this. You're going to have ones along your diagonal in the first part and zeros everywhere else. And then the numbers on the right side are going to be your inverse matrix. So this is what we're going to start. We're going to take our original matrix, our 3x3, and those numbers will be here. We're going to fill in the right side with this matrix, ones along the diagonal, zeros everywhere else. And we keep doing row operations until we got ones and zeros down the first. And well, zeros and ones everywhere here. We're going to make it look just like that on the left side. What we end up with on the right will be our inverse matrix. I think this is number 4, I'm not sure. All right, in your directions, they may, or you may see this, like it may say, well, what they're going to call this is A, and then they might say I sub A. All they're saying is this is matrix A that you're starting with, and they call this the identity matrix of A. So if you see that, it's simply the identity matrix of A. Then they're going to tell you all right, so find A inverse. All right, so we're finding an inverse of a 3x3. So the first thing you're going to do is write that, and you could have just done it out to the right of it as you're there. All right, so on this right side, you fill in with the identity matrix for a 3x3. So I'm putting ones along that diagonal. Okay, so essentially what we're working with all the way through this problem is a 3x6 matrix. Okay, the first thing we have to do and it's a little bit less work on you, somewhat. We have to focus on, this goes back to that Gaussian method, Gauss-Jordan method from 8-1. We have to make this first column ones and zeros all the way down. Well, it already has 1 and 0 here, so we have to focus on getting -2 to become 0. You can't use row 2 because it has 0 there, so 0 times anything like is going to be 0. So that will not help you eliminate this. What can you multiply row 1 by? Good. So let's multiply row 1 by +2, and I'm going to add it to row 2. Go ahead. Before you do anything, I would go ahead and write the rows that do not change. Like row 1 does not change. As well as row 3. All right, so do this in your head as you go. Multiply row, we're gonna multiply every one of these numbers by +2. Add it to each of these numbers in row 1. I mean row 2. Sorry. All right, so if you go through and I'm gonna multiply this by, crap. Which row are you adding that to? Was anybody gonna tell me? That's good. Sorry, I'm so sorry. This is already confusing enough without me throwing you guys off. We're wanting to change row 3, so we're gonna multiply row 1 by 2 and add it to row 3. So sorry. Okay, so row 2 doesn't change. Okay. This times 2 plus that will give you 0, which is what you want. This times 2 is -2 plus -3, -5. That times 2 plus 0, 2. This times 2 plus 0 is 2. And then that times 0 is going to give, that times 2 is going to give you 0. So 0 plus 0, 0 here, 0 plus 1, that's going to stay, they're going to stay 0 and 1. All right, once we get these two columns to become zeros and ones, then this matrix left will be our inverse. Okay. All right, in this, now let's focus on the second column. We want this to be 1, those to be zeros. What could you go through row 2 and multiply by? How are you going to make this +1? We're going to multiply row 2 by a -1/2. Row 1 stays. Row 3 stays. All right, this will stay 0. If I multiply this by -1/2, I get +1. This times -1/2 that will be 0, that will stay 0, and then this will give you negative 1/2. Okay, so that's where we're at to that point. How are you, let's change either this is 0 or that, doesn't matter. Tell me what we multiply row 2 by to change. Well, let's add, what rows can you add together right now? Good, add row 2 to row 1, because that will give you 0 in this spot and this will stay. So as long as that first column doesn't change, we're good. So row 1 stays. Row 2 stays. And row 3. It's a lot of work. So 1, 0, and then we got, I'm going to add all of this, so negative 1/2 plus 1, that'll give me a positive 1/2. 0 plus 1, that stays 1. Negative 1/2 plus 0 will give me a negative 1/2 here. And then 0, 0, that will stay 0. Are y'all okay so far? Okay. It's a lot of work. I told you you're not going to like 3 by 30 inverse. How are we going to change negative 5 to 0? All right, now let's go through and multiply row 2 by positive 5, add it to row 3 to get 0 here. So this becomes 0. And then you have negative 5/2, which is also negative 2.5, and then plus 2. So that's going to give you a negative 1/2. This times 5 is 0, so that's going to say 2. That will give you negative 5/2 plus 0 is negative 5/2. And 0, that's going to stay 1. Okay, we're getting very close to being done, finally. But we need this number in column 3 to become positive 1. So what do you multiply row 3 by? I need that to become positive 1. So we're going to multiply through by a negative 2. Have I lost y'all? Are y'all good? All right, go through and multiply everything by -2. This will give you +1. This will give you -4, +5, and -2. All right, a common mistake I see people make from this point is they want to add like these two rows together to get 0 in either spot, but you can't do that because it will change. For example, if I add row 2 to row 1, then this will turn to 1. So you've got to make sure that your row operations leave what you've done previously. Okay, so let's change row 2 or row 1 to make these zeros. All right, let's say I want to focus on row 2. So let's multiply this by what? Multiply row 3 times a +1/2 and add it to row 2. Okay, so 1 times that plus that is going to give you 0. And then this times 1/2 is going to give you -2 plus 0, -2. 5 halves minus 1/2 is going to give you 4 halves or 2. And then 1/2 times 0, so this is going to say 1/2 times -2, sorry, is going to be -1. -1 here, and then you add it, so -1. Okay, one last thing to do, and then we'll have our inverse matrix on the right side, finally. All right, tell me what we're going to multiply row 3 by to get this 0. -1/2. All right, so let's start here. We know all of this prior should stay the same. So if I multiply that together, -1/2 plus that, we need 0, which is what I want. And then -1/2 times -4 is -2 plus 1 is -1. -5 halves minus 1 more half is -6 halves or -3. And finally, -1/2 times -2 is +1 plus 0 is 1. So now that you arrived with this result on the left side, A inverse is that matrix. Don't you guys love a 3x3 inverse? It's terrible, isn't it? I mean, that literally took me, let's see, which I'm writing pretty big, but still. Took me pretty much almost 2 pages to do. The math involved is not hard, it's just extremely long, as you notice. Just be thankful I'm not making you do a 4x4 inverse. Like that's just, it's hideous. Even worse than this. All right, I'm gonna go back over some of that, or I'm gonna hit like an example of each next week too. And then we'll look at the area of a triangle using inverses, which you did last year as well. But I'm just gonna call it a day on that one.